Okay, here's the second video. Let's wrap up this marathon lesson. We're continuing to simplify radical expressions. And number 14 here, like the previous problem, is one where we're going to need to rationalize the denominator. So what I would do is rewrite the denominator as the fifth root of 2 to the third power. And then let's find our special form of 1 that we want to multiply by. So we have 2 to the third inside the radical. We're going to have to multiply by a fifth root of something. So let's make it 2 squared, because that way, altogether, when we multiply the denominators, we have the fifth root of 2 to the fifth, and that's just going to be a 2. And then our numerator is going to be the fifth root of 7 times 2 squared, which would be 7 times 4, so fifth root of 28. So we have fifth root of 28 over 2. Okay, the next couple of examples are involving subtracting. It could be adding or subtracting radicals. So you need to have like terms. So just like if you were doing something algebraic and you had, say, 7x minus 3x, these are like terms, but 7x minus 3x squared are not like terms. Well, in order for radical expressions to be like terms, you would have the same kind of radical, like both fifth roots, with the same number on the inside of the radical, same radicand. And that's what we have here in number 15. We have 7 times the fifth root of 12 minus 1 times the fifth root of 12, and 7 minus 1 is 6, so we have 6 times the fifth root of 12. So that one was easy, but what about number 16? Both of them are cube roots, so we have that, but they don't have the same radicand. They don't have the same number inside the radical. However, it might be possible to simplify one or both of them, and then we'll check to see if they have the same radicand. So the cube root of 81, let's see, 81 is 3 to the fourth power, which is 3 cubed times 3. So that can be written as 3 times the cube root of 3. And the cube root of 24, that's the cube root of 8 times 4, or 8 times 3, and 8 is 2 cubed. So we have 2 cubed times 3. So this one can be written as 2 times the cube root of 3. So notice that since we've simplified, we do have the cube root of 3 in both terms. So we subtract. 3 minus 2 is 1, so we get 1 times the cube root of 3. And since we're doing all this work with cube roots and fifth roots and so on, I thought I would make sure you know how to find a calculator key to find any kind of root you want. So here's my calculator. Let's say I want to find excuse me, the fifth root of 32. So one option is to go into the math menu and to choose number 5, the xth root. And then you can type in the kind of root you want, that's the index, and then you can put your 32 in there. Now some keys have a shortcut. If I press alpha window, notice that's a shortcut. It also has the xth root button, number 6. So alpha window, number 6. It's not a whole lot shorter, is it? But sometimes that menu is a shortcut for things. And then another option is to use an exponent. So you could do 32 raised to the power of 1/5, since we know that the 1/5 power is the same as the fifth root. So you can do it either way. Okay, let's keep going. All right, we're going to be looking for a pattern here. So I have a bunch of numerical examples to lead us to that pattern. The square root of 2 squared is just 2. Square root of 4 is 2. What about the square root of negative 2 squared? Again, it would be the square root of 4, which would just be 2. What about the cube root of 8 cubed? Well, that would be the cube root of 216. That would just be 8. I think it's 216. I don't know. That feels right, but I'm not sure. What about the cube root of negative 8 cubed? Now, are we just letting the root and the power cancel each other? Like right here, does the cube root cancel the cube, leaving you with just 8? Yes. Here, does the cube root cancel the cube, leaving you with just negative 8? Yes. Up here, does the square root cancel with the square, leaving you with just 2? Yes. But what about this one, the square root and the square? They don't just cancel, leaving you with negative 2. So it's not as simple as that. It depends on a couple of things. Let's keep going and see if we can figure out what it depends on. The fourth root of 3 to the fourth would be the fourth root of 81. That's just 3. But the fourth root of negative 3 to the fourth is also the fourth root of 81, so that's also 3. It's not negative 3. The fifth root of 4 to the fifth would be 4. The fifth root of negative 4 to the fifth. Well, negative 4 to the fifth, whatever it happens to be, is going to be negative, and its fifth root would be negative as well. So, it depends on a couple of things as to whether or not the answer you get is the same as the original input, or if it's the opposite. If you have a positive number here, you're always just going to get that number back out. But if you have a negative number here, it's going to depend on if your powers and roots are positive, or are even or odd. When they were odd, you can have an odd power with a negative result. You can have an odd root with a negative result. Put a negative in there, get a negative out. But if you have an even power with a negative number in there, you put your negative number in there, you raise it to an even power, now you have a positive. Take an even root, you have a positive. So it depends on the kind of number you have inside, the kind of radicand, and the kind of exponent you have. So if n is odd, if the power and the root is odd, you can have a negative result, you can have a positive result, either one works. If x is positive, you get a positive. If x is negative, you get a negative. You just get x. However, if your root and your power are even, you're always getting a positive result. If you put a negative number in for x, you get a positive result. If you put a positive number in for x, you get a positive result. So you get the absolute value of x. Now, we could do a bunch of problems where we simplify and include the absolute value signs, which we're going to do a couple of them. But typically what textbooks will do is they will just say, well, let's just assume that our variables are all positive and then we won't have to worry about it. So let's go ahead and practice with absolute value signs on this one. We have the fourth root of 625, z to the 12th. Now 625 is the same as 5 to the 4th power, and z to the 12th power is the same as z cubed times z cubed times z cubed. Oops, that's not what I meant, is it? What did I mean? Z to the 4th times z to the 4th times z to the 4th. That's better. So the fourth root of 5 to the 4th is 5. The fourth root of z to the 4th is z, or is it? Well, it depends on if z is positive or negative. And then we have it again, and we have it again. So the problem is, if z is a negative number, and we don't know what z is, if z is a negative number, if you raise it to the 12th, you get a positive, and you take the fourth root, you get a positive. We actually need this to be positive. So we are going to need those absolute value signs around it. You could do it like this, or you could do it like this. They are going to be the same thing, either way. And how about number 18? This one I gave you as an exponent, in exponent form, but you could think of it as a radical, either way, same thing. And because we have an odd index, we have a fifth root, we're not going to need absolute value signs. The fifth root of 32 is 2, the fifth root of m to the 5th is m. If m is positive, that'll be positive, and if m is negative, that'll be negative, and it works out either way. And then the fifth root of n to the 30th is n to the 6th. And that's going to be positive no matter what. Okay. So, getting close to the end here, we're just going to do some various kinds of simplifying, and this time it says assume all variables are positive. So we're not going to worry about absolute value signs. Okay, so when you look at number 19, what you have to realize is that 56 is not married to A. It's 56 times A times B to the 3/4. 7 is not married to A either. It's 7 times A to the 5/6 times C to the negative 3rd. So you can do things with 56 and with 7 independent of the letters. 56 divided by 7 is 8. A divided by A to the 5/6, subtract the powers, you get A to the 1/6. There's only a single B, there's B to the 3/4, there's nothing to combine it with. And then the c on the bottom as c to the negative third could be written as c to the third on the top, and that way we won't have any negative exponents. Number 20. Again, the 6 is not connected to the x to the 4th. These are all separate. 6 times x to the 4th times y to the 9th times z to the 14th. Treat them all as separate factors. Is there any perfect cube that we can pull out of the cube root? Well, 6 is just 2 times 3. There's no perfect cube there. You can think this. You don't necessarily have to write it, but x to the 4th is x cubed times x, so there's a perfect cube. Y to the 9th is y cubed times y cubed times y cubed, so there's 3 perfect cubes. And z to the 14th is z cubed times z cubed times z cubed times z cubed times z squared. So pulling out the perfect cubes, x cubed, y cubed, y cubed, y cubed, z, 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 z. Okay, we are going to have x on the outside, y, and y, so y cubed on the outside, z, 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 and z, so z to the 4th on the outside. And then what's left inside the cube root? We have the 6, we still have the x that we didn't use, and we still have the z squared. Okay, now here's a quotient, and so we'll have to rationalize the denominator. We can't simplify p to the 8th over q to the 5th by reducing p over q. We could think of this as a separate numerator. Oops, let's make that a p. We could think of this as a separate numerator over denominator, and we could simplify the numerator first if we want to. That would be p times the 7th root of p. But we still have to rationalize the denominator. So remember, we find that special form of 1 to multiply by, so that the denominator just becomes q. So we need a 7th root. We need q squared to multiply by q to the 5th to give us q to the 7th, which will have a 7th root of q. So our special form of 1 is the 7th root of q squared over itself. So then putting our numerators together, we get p times the 7th root of pq squared, and then that is over q. Okay, this is going to be the end. What we need to do is just put some of this into practice with solving equations. So we have 6x cubed equals 384. Let's divide both sides by 6. And that's going to be, what is it, 64, I think? And then cube root. Now, when you cube root both sides, do you need plus or minus, like you did when you square rooted both sides of an equation? No, you do not, because the cube root of 64, there's only one number, 4. It's not plus or minus 4, it's just 4. And how about number 23? So the way to undo the 5th power is to take a 5th root of both sides. So we could write that as the 5th root of 100, or 100 to the 1/5 power. And then to get x by itself, we're going to add 8 to both sides. So the exact answer is written as 8 plus the 5th root of 100. I don't think we can simplify the 5th root of 100. And you could get an approximate answer using your calculator, but we weren't asked for an approximate answer, so I'll just leave it like that. Finally, we've made it to the homework, and it does look like a lot. There are more problems than you typically have, but most of these problems are really short without really very much work to show. So I have shortened the assignment compared to what I normally give. I hope it's going to be manageable. Thanks, everybody.